On October 19, 2016, the Schiaparelli lander crashed on Mars. The European Space Agency attributes this failure to bad data from the inertial measurement system. The computer collected data from multiple readings, and from a negative altitude, the onboard computer thought it meant the lander was on the ground or about to land. Retro rockets were only activated for a slight period of time. The parachutes were deployed and injected, and on-ground systems were activated. Instead, the lander was 3.7 kilometers above the surface. Modeling and simulation replicates environments in which systems like this can be tested and experimented with. This saves on cost and embarrassment, and in other applications, lives. But how are these models tested? How do we put models into environments that expose failures? I'm Matthew McLaughlin, and with me is Hassam Sarjugian, and our research focuses on testing DEVS models. DEVS stands for Discrete Event System Specification, a type of modeling and simulation specification that is formalized with mathematics, has strict requirements on modeling, and offers a structured system specification through input-output ports. This research pulls definitions, techniques, and methods from a lot of different sources. Therefore, I will provide a little background as I move through each. I first introduce DEVS and its various specifications, including a specialization of the experimental frame called a test frame. I then discuss established testing methods and practices. Then, multi-threading and synchronization. I then bring all of these topics together into the test frame atomic model and discuss its design and implementation within DEVS Suite. I demonstrate the test frame's integration effort with JUnit and DEVS Suite framework. I conclude the introduction by discussing related work. Finally, I demonstrate a use case. This use case is included in the current version of DEVS Suite. Though this testing framework is implemented in DEVS Suite, the test frame should be considered a DEVS model in and of itself, not tied to any particular DEVS simulator. That is the originality of this research. We combine scripting and DEVS formalisms and set out to prove this marriage does not need to break DEVS semantics. We then focus on testing as just one application of this union. DEVS scripting depicts the behavior of a DEVS atomic model through a script in a separate thread. We aren't using multiple threads to reap the benefits of parallel processing. We are using it to keep a persistent stack frame so we can write simple scripts. This has some unique advantages, but is not very scalable. If we had 1,000 scripted models, we'd have 1,000 threads competing for the same resources. Therefore, our focus will be on the test frame and its implementation. This removes scalability as an issue because one test frame typically facilitates the entire test case. At the core, we follow the parallel atomic DEVS I/O formalism. Note that the only state transition functions that can alter the state of the model are shown by the S. This is important for ensuring DEVS scripting is compliant with existing DEVS specifications. We accomplish this by blocking the thread until we enter one of the state transition methods. DEVS specifies the composition of models here. It has closure under atomic DEVS, which allows coupled models to contain atomic or coupled components. Modeling in DEVS offers multiple layers of abstraction because of hierarchical composition. Experimental frames specify the conditions under which a system or model can be experimented with. Testing also has conditions. Tests have a setup phase, similar to a transient state, inject inputs, and receive outputs from the system. Tests have all of these roles. However, testing focuses on pass-fail as the primary metric. Those roles are depicted on this slide. The design of our test framework ensures all elements of testing may be kept in one place to ensure rapid development of test cases and diagnosis of failing tests, and also the reuse of the test frame. This requires a test frame to also be responsible for developing a test fixture, placing itself and the model or models under testing inside the test fixture. Due to the nature of DEVS, the models we test are black boxes. We cannot prove a state change happens. We can only observe I/O. Consider a simple processor, one input, one output. If I give it a job to process, how do I know it accepted it and started processing it? I can't. It's considered a black box. I cannot observe state transitions. I can only wait until it returns the completed job. Once a test frame receives the completed job, it can inspect it. If the test frame doesn't receive any completed jobs, it can fail the simple processor test. It's up to the programmer to trace the issue. This is the weakness of black box testing. The black box could have numerous state transitions and cover a lot of code before the output is generated. There are a lot of techniques for black box testing, most of which require some requirements model to extract inherent complexities and logic from. Here are the advantages and disadvantages of scripting a model's behavior in a separate thread. A Stackframe maintains a call structure and local variables even while the thread sleeps. This reduces the complexity of behavior modeling. However, it's not scalable. This isn't a problem for testing. Models under testing interact with one test frame. If multiple test frames try to interact with a model at once, testing would not be well controlled or independent. Synchronization is also a challenge for any multi-threaded software. Ours has a unique requirement on synchronization to conform with parallel atomic DEVS specification. The nest lock combines two semaphore locks, an entry lock and an exit lock. The outer thread releases the entry lock so the inner thread can run. The inner thread releases the exit lock so the outer thread can resume. This has an effect of embedding the code from the inner thread within the outer thread. The inner thread plays the role of the test script, and the outer thread plays the role of the state transition function. Here we show the main loop for the DEVS simulation. I emphasize that the model's delta function must return to the simulation thread before time can advance on the model. If you are going to run from an interactive script that interacts with other models, it cannot exit. The solution calls for two threads. Someone might argue that you could write a pure DEVS model to do what this test frame does. That's true, but there's a beauty to maintaining a stack frame. For those who may not be familiar with the role of a stack frame maintains local variables and the location each function from the backtrace will return to. Each thread maintains its own stack frame. However, local variables are lost and we cannot hold our location in a test script if we have to exit the test script each time. Each code block represents code that interacts with the simulation. This can be sending or receiving messages to or from other models, or to just simply wait. With DEVS scripting, testers can write code sequentially in one test script. A pure DEVS approach is shown on the right. Also, note that the output function will have a similar switch statement. The location in the test script is squirreled away in some kind of sequence indicator or phase, as well as other local variables. Depending on the interaction with the simulation, we enter the pure DEVS test frame model through either the internal or external state transition method. Then we enter a switch statement with multiple branches, run that case, and exit. This approach adds unnecessary complexity, and when testers write code with multiple branches, mistakes are made. If we run a test and it fails, I'm betting the bug is in the test frame on the right and not the model we are testing. The test frame atomic model hides this complexity by implementing the state transition functions, so that testers can derive from it and write more sequential code. The test frame was designed to be extensible. It can be used for testing one or more models, even evaluate one or more implementations. A robust set of scripting methods are made available that try to mimic commands one might see in a software test plan, such as inject an input, wait for an output. We also want to fully support confluency and super dense I/O testing. To integrate test frames within JUnit, a test factory is employed that finds all test scripts and generates a simulation for each one. Assertion errors are raised in the test script for easy debugging when running under a debugger. Another tool for testers is DevSuite. Testers can visualize the message traffic, see inside the black box, plot input, output, and state trajectories. Since there is a great amount of research in the topics of DEVS and black box testing, we need to enumerate what makes DEVS scripting a relevant and important addition in this area of research. Our test frames are DEVS derived, allowing us to reap the benefits of a DEVS simulator, such as any structural visualization, animated port-to-port message traffic, logging, and trajectory graphing. The benefits of scripting also carry over from regular software testing. The difference being, the script does not execute the model. The simulator executes both the model and the test separately. Because of that separation, a thread is used to maintain the stack frame for the script. From this concept, we further explore its benefits to debugging failing tests for the programmer assigned to fix it. A collection of factory models and their test frames are demonstrated in this release of DEVS Suite. Their requirements and design are offered as a separate document to better understand how testing methodologies translate into our test framework. We develop a simple processor, FIFO buffer, workstation, and CONWIP model. CONWIP stands for Constant Work in Process, a computerized control system that keeps the number of jobs constant within a system. This is a UML class diagram for the CONWIP model. On the left, we have the model design, and on the right, we have the design for the tests that will be conducted. The other models for our production system will have a similar setup, with the distinction between model design and test design. The design for the test framework is shown here. The scripting methods are shown on the left. Now this is a high-level abstraction since the return types and parameters are left out. Instead, we are emphasizing the extensibility of the test framework as shown on the right. The models and tests have been implemented. Here is the CONWIP test script to ensure the backlog has FIFO ordering and trajectory graphs with respect to CONWIP I/O. The CONWIP has a target whip of 1. So the first job is immediately released. The other jobs leave as a response to the release command. This test also demonstrates that CONWIP does not model time. It represents a computerized control system. Responses are immediate, but appropriately sequenced. No simulation time has passed in this time view. Since the test fixture and its components are DEVS models, the simulator displays them just as it would any other DEVS models. As I click through, you'll see the first job enter the system. We have a target work in process of 1, but currently do not have any processes being worked. So the next step will release the job into the production system, bringing our current work in process to 1. The next 2 jobs will be dispatched to the CONWIP and be added into the backlog until the test frame sends the first job to be released. It reduces the current work in process into 0, and the next step should show the next job be released. Test frame captures it. It sends the second job to the release, and the third job should be released. Now it sends the third job to be released, bringing the CONWIP back to its initial state. This is not important here, but I have the ability to run a collection of sequentiable tests. The CONWIP passes the test. I have the pass-fail message just for the user. If we run in JUnit, failure is thrown to JUnit to capture. At a higher level of testing, this test framework could be used to test emergent behaviors from connecting multiple systems. Any manufacturing engineer could look at this factory, identify bottlenecks, and predict where the production system would fail and at what threshold. We can build test scripts at this level to test behaviors exhibited at system-level abstractions. Our test frames can be integrated with JUnit, and this figure shows the results that Eclipse will give you. As each code change is made, we can rerun all of the automated tests to verify this change does not break other models. Code coverage is one metric to measure the quality of testing we are performing, and I will show an example of this on the next slide. Another use for keeping these tests around is to run dynamic checks on them. Dynamic checks can check for things like leaked or mismanaged resources. The test may not fail, but problems can be identified that throw errors later. Here is my code coverage report for the conwip model after running all tests. I can see from the yellow lines I should have considered writing more test cases for invalid partitions. Those model side assertions are probably just written proof of my paranoia, but I don't consider them part of code coverage. I mentioned debugging being easy in dev scripting. That is because the failure trace can point me to the location in my test script where the failure was thrown. That location is shown by the red arrow in the lower left. If I click it, I get the code shown on the right. I've highlighted some possible interactions that the model under testing may have failed to handle on the right. Failure to receive on in, failure to receive on release, or failure to send the job back. If I add a Java exception breakpoint as shown by the toolbar above, I can halt the program and hover over variables to see their values, as this may help in diagnosing the failure. These local variables are lost if the Stackframe were not maintained. I can also run the test in DEVS suite and visually verify the animated messages or trajectory graphs. I can hover over the conwip model and see into some of the state variables just before the exception. Let's begin this demonstration with running our regression testing. We can see here that the factory tests failed. Well, that's a coupled model that integrates the conwip with some buffers and processors. It tests that the models are properly coupled within the factory, as well as high-level emergent behaviors. I will need to see if any atomic models fail before I attempt to debug the factory. Aha, the conwip, and nothing else. It fails most of its tests. Whatever the problem is, these all have it in common. I know the test for FIFO is pretty straightforward. I'll start there. The failure trace is very useful. The top row is the assertion failure. I can skip down to the test frame, and Eclipse will take me straight to the script. The failure is under read output. I would venture to say it is one of these possible locations. Either jobs weren't being accepted by the conwip, or they weren't being released. Let's say that I'm not very good with coding. I want to see what's happening. I'm going to launch the simulation and run this test in it. Here we are. Target WIP of 1, nothing currently in process, no backlog, and the model is passive. The first job is sent. Based off the conwip behavior, the job should be sent out to be processed on the next set. There it goes. The script also sends the next job. One job being worked. This job 2 is in the backlog. So far, so good. One job being worked, 2 jobs in the backlog. Clearly the conwip has no issue accepting jobs. Now we have a message to a different port, this time to release. I should see job 2 leave on the next step. Nothing. Well, that's our failure. I bet this narrows it down. Everything looked good from what I observed. Jobs were being accepted, and one job even left the conwip for processing. After the release command, the behavior didn't match what I expected. I'm going to start with DELT-ext, because that's where the release command starts. Jobs added on in. We don't even use set in this test. Job released on released port. Wait. I sent the job on release. I'm not seeing the issue, or it's not jumping out. I know the job starts with the release, so I will break on DELT-ext. Well, let's try again. I'm here. But it's for the import. Note that I ran debug for all of Conweb, so I may be in another test. If I go through the threads, most have jobs, but the test frame should be stuck in a nest lock. Here. I'm in the backlogged test in this inject. Here again. Still on in. Here's the release. Good. Next step, I will enter this code block. No? Release, released. Oh, an extra letter. That's tricky. I'm confident this will address many issues we've seen. Let me rerun the regression testing. Nice! Until this point, the test frame has made no assumption about how the simulation and coupled coordinator function. The models under testing could be remote, simulation time could be real time, and simulation events may run in parallel. If the test frame contains all elements of testing, it should have a reference to the model it tests. Can we open the black box and peer inside using some agreed-upon interface? After all, this could lead to a better scope of testing since we can test each arc from that requirements model individually. Back to the black box test frame. It is derived from a parallel atomic DEVS, and though it is multi-threaded, it does not break DEVS semantics. We have proven this through synchronization and nesting state variable changes only within state transition functions. Through synchronization, it is also repeatable. Specifics about the test frame design were motivated by good testing practices, such as low complexity in test scripts, and keeping all elements of testing in one place. We also demonstrated a support for system-level testing and testing emergent behaviors. We have a DEVS scripting test framework developers manual at the Arizona Center for Integrative Modeling and Simulation website. This guide also contains the production system use case, discusses testing practices, and follows each model and their tests through design and implementation phases.